Today we're going to take a look at section 1.10, which is radical expressions. This section is a longer section, both for me to teach to you and for the homework part of it. So just sort of be prepared for that, that this is going to take you a little bit longer. And for my other class, that's an intermediate algebra class like you guys, it was the section that they found the most challenging. So just be aware of that as well. So if you haven't already come to visit me in my office, or if you haven't gone to the Success Center, you might find yourself in need of a little bit extra help on this one because it is a little bit more of a challenging section. So I'd like to take a look with you first at what we mean when we talk about radical. So you'll recall that the square root of 25 is 5, right? We talked about square roots in the very first section of material, but we didn't really look at finding exact or sort of broken down pieces when things weren't perfect. Like 25, square root of 25 is 5, and that's great. The square root of 50 can't be broken down quite so nicely. The best that we did back in the first section is we said, well, it's between this value and this value. But we're actually interested in this section in breaking square root of 50 down into a simpler form. And the way that we do that is we do that with factoring. So what number or numbers, just give me two numbers that multiply to give you 50. Okay, 5 and 10, that'll work. Sure. 5 is prime, so we don't break it down any further, but 10 is not. 10 is actually what? 5 and 2, right. So I could actually take the square root of 50, and I could rewrite it as the square root of 5 times 5 times 2, right? Sure. Now, what we do when we're looking for square roots is we look for two matching terms underneath the radical, and we're able to pull them out one time. Notice that's what happens with 25. 25 is 5 times 5, so we pull out a 5. And there isn't anything left underneath the radical to write. There's a 1 that doesn't actually need to be written, so we simply write it as 5. On this one, though, we actually pull out our 5, and there's still a 2 left underneath the radical. So the square root of 50 is actually 5 square root of 2. But I'd like to show you why. So that's actually problem 1. I don't know if you guys noticed it as I was doing it. I'm sorry for not flipping my screen. This was 5 square root 2. But I'd like to show you why it actually works with this one back on my other screen. So the reason that the square root of 25 is 5 is because 5 times 5 equals 25. That's why. It's actually the same for the square root of 50. The square root of 50 is actually 5 square roots of 2, because if I were to multiply 5 square root of 2 times 5 square root of 2, I would multiply the values on the outside. What's 5 times 5? 25. And then I'd multiply square root of 2 times square root of 2, which would be square root of 4. What's the square root of 4? 2. And what is 25 times 2? 50. It's the same 50 that was underneath the radical to start with. Okay, so it works for the exact same reason that square root of 25 is 5. It's just that there's still a remaining piece underneath the radical that I can't pull out or simplify any further. So as we're taking a look at each of these, what we're going to be doing is we're going to be breaking down the number that's underneath the radical into either matching pairs, if you find something sooner, or if you don't find it soon enough, then all the way down into primes, okay? So sometimes we'll find something more quickly. For example, let me just do one real quick so you can see. Let's say that we had 200. Whoops, that's not what I meant to do. Still not what I meant to do. There we go. 200. And you broke it down and you were like, hey, 200 is 2 times 100. And you were like, 100 is 10 times 10. Well, the 10s are not prime, but they match at this point. So I don't necessarily need to break the 10s down any further because I have a matching pair that I can pull out. But if I don't necessarily see a matching pair before, then I would keep breaking things down, okay? So let me take a look with you then at 48. So we're going to break 48 down. What two numbers would multiply to give you 48? 6 and 8. Okay, they don't match, right? And maybe you broke it down in a different way. It's okay if you did. We'll get to the same point in the end, I promise. They don't match, and neither one of them are prime, so we're going to keep going. So what is 6? 3 and 2. And what is 8? 4 and 2. I'm going to write it over here like this, actually. 4 still breaks down further. It breaks down into 2, and 2. So if I come back and I check them, I've got a 2, a 2, a 2, a 2, and 3. So I'm going to rewrite this one as the square root of, and I had 2, and 2, and 2, and 2, and 3, in whatever order you'd like. And we're looking for matching pairs. So you should see a pair of matching 2's and another pair of matching 2's. Each pair of matching 2's will come out. So on the outside I brought out a 2 and a 2, and underneath is still a 3. What is 2 times 2? 4. So this is 4 square root 3. We didn't ignore the 4. We broke the 4 down right here into 2 and 2. That's why. If you had done 48 in a slightly different way, like maybe you looked at that and you saw the 4 to begin with, that'd be okay. And then the 48 is actually 12. You could also go from that perspective. You could keep breaking things down from there. So it doesn't necessarily have to be broken down into 6 and 8 to start with, if that's not the one you see. You can go with any 2 factors that will actually break it apart, okay? Let's try with 45 now. So how will 45 break down? I realize that there's an x to the 4th there. We'll have to talk about that separately, but whoops. 9 and 5. All right, so I'm just going to make this a little bit smaller. All right, good. 9 and 5 looks good. 5's prime, so can't do it any further, but 9 is 3 and 3. Okay, so underneath here, the numerical part is now 3 times 3 times 5. And what I actually have is I have 4 x's, like that, right? That's what x to the 4th means. So I'm looking for pairs. Well, there's a pair of 3's. What else are there pairs of? Yeah, there's 2 pairs of x's. So I'm going to bring out a 3 and the first x and the second x. But there's still a 5 underneath the radical that doesn't get to come out because he doesn't have a matching pair with him. X times x is actually x squared, and then my square root 5. Okay, how are we doing so far? All right. Okay, we're going to do the same thing now with the number 12. 12 is what? 4 and 3, all right? 3 is prime, 4 is not, so I need to do 4 to be 2 and 2. So again, I'm just looking at the primes at the end if I've got them factored all the way down like that. So this would equal, okay, let me make this smaller again up above. So okay, all right. So the 12 is 2 times 2 times 3, and then I have y cubed, so there's 3 y's. All right, so what do you see matching? A pair of 2's and a pair of y's. So the 2 will come out, and the y will come out. What remains underneath? The 3 and the leftover y. So sometimes I end up with variables still left underneath. Sometimes I don't. It just depends on how many of them are there to begin with. All right, so we've been going on some basic ideas without actually defining them as of yet. This radical notation that we have. And radical notation actually has more pieces than we're sort of giving it credit for at the beginning here. So the radical notation actually looks like this in general. Okay, there's a little n that's sort of inside of the radical corner right there. That n is called the index. Of course, the square root that we've been using is actually generally called a radical. And the value that's underneath it is actually got a name too. It's called a radicand. All right, here's the catch. We've not had any number in the little corner where the n is so far, have we? No. So when the n is missing, right? It just doesn't show up. It's understood to be a 2, which is a little different. Most of the time when we don't have anything in a location, it's an understood 1, right? No number in front of the x, well then it means it's 1x, right? Well, on radicals, when there's no number in that little corner of the radical, it's actually understood to be a 2. That's why we're calling it a square root. That's why we're looking for pairs of things, is because there's an understood 2 there. So when we did a moment ago, this, it's actually the same thing as having this. There's an understood 2 there. And in fact, every single problem that we did, 1 through 4, were understood square roots because they had no number in that corner. So let's actually take a look at what happens when we don't just have a square root, but instead we have some other index in our problem. So on number 5, what you see is you see a cube root. There's a 3 index there. So the thing is that it works the same way. We're still going to break it down. And so 16 breaks down how?
8 and 2.
Okay, 8 and 2. 2 is prime, so what's 8? 4 and 2. Again, 2 is prime, 4 is 2 and 2, right? So this is the cube root, and I actually have 4 2's underneath here. Okay, so far I haven't done anything different, right? Exactly the same thing. The difference is that while over here I was looking for pairs because it was square roots, on this problem I'm going to be looking for 3 of a kind, right? It's like playing cards or something like that. Right? We're looking for 3 of a kind because it's a cube root. So as long as I have 3 that match because of the cube root, I will pull it out one time. So there's a 2 on the outside, there's this 2 still underneath, and you still need to remember to write that it's a cube root of 2 that's left. The index doesn't go away. So this is 2 cube root of 2. Now just like with square root of 25, and we found out it's 5, we said, oh, that's because 5 times 5 is equal to 25. If you wanted to verify this, what you would do is you'd have to multiply it by itself 3 times. So you have to multiply 2 cube root of 2 times 2 cube root of 2 times 2 cube root of 2, because it's a cube root, right? And you should get back, of course, to 16, and you would. But this would be a cubing process instead of a squaring process to get there. We're going to do the same thing for 256. That's probably a little bit less common of a number for you. It's a little bit bigger. So what will 256 break down into? 6 and, what did you say? 16 and 16. Fabulous. It's a perfect square, but we're not looking for squares, right? So that's good. It's 16 and 16. We just did 16s, didn't we? Yeah, they're both 4 and 4. And each of my 4s are 2 and 2. Thank you, Malik. Lots of 2s as my examples. How many 2s, in fact? 8 2s. All right, so I have 2 times 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 2. Did I get them all? Lovely. How many is it going to take to pull it out? Not quite. 5. Why, Anya? Yeah, this right here is a 5th root, so it tells me I need 5 that match. So I have these 5 2s, and they will come out again one time. So there's 1 2 on the outside, and underneath I'm left with 2 times 2 times 2. What is that? It's 8. And it's perfectly reasonable that we would multiply that back together because it doesn't simplify to come out. So this would be 2 5th root of 8. Cool stuff, right? Yeah, absolutely. All right, so I mentioned something before. This is a little bit different. We haven't seen a problem quite like this. But we're going to be dealing with what are called like terms. We do like terms within algebra. We'll see them further in sections 111 and 112. But right now when we're talking about like terms, we're specifically doing this in reference to radicals. So like terms, when we're referencing radicals, are going to be two or more terms involving radicals that have the same index and the same radicand. Okay, radicand means the stuff that's underneath the radical, and index, of course, is that corner number. So I can't combine a square root and a cube root. They don't have the same index. I can't combine square root of 2 and square root of 3 because they don't have the same radicand. Okay, so they have to match in their index and they have to match in their radicand. All right, so let's do some examples for like terms.
What was the second one in that one?
Radicand, maybe? Index and radicand? Yeah. You bet. Okay, so on this one, do they have the same index on number 7? Yes, they're both square roots, right? Yeah. Do they have the same radicand, the number underneath? They do, they're both 3s. So since that's the case, this is saying that I have 6 of these and 2 of these, and I'm subtracting. So what is 6 minus 2? 4. So this is 4 square root of 3. Okay? You can think of it, in fact, oddly enough, you're far more comfortable thinking of this like 6x minus 2x and being able to tell me 4x, right? I mean, that's the same question. It's just that instead of having x's, I have radicals that match. So I'm still allowed to do the same sort of thing. I'm combining them. They are like terms. Now, 18 and 27. They're both square roots, right? But those radicands do not match. Agreed? Now, before you just write it off and say, well, there's nothing I can do and I'm done with the problem, hopefully you do recognize that 18 and 27 do simplify. Right? They're not prime numbers like the square root of 3 that I just had a moment ago. So I need to break them down because it might be possible that as I break them down and simplify them, that their radicands will eventually match. So that's what we have to check for. That doesn't mean they will have to, but they might. So we're going to check. So what is 18? 9 and 2. And 9 is 3 and 3. So let's actually do this piece first. I already have a 2 on the outside. And now I have 3 times 3 times 2 underneath. I'm looking for matching pairs, right? The 3's match, so they'll come out. There's already a 2 on the outside. Now there's a 3 as well. We multiply them, and I'm left with a 2 underneath. So this is 6 square root 2. All I've done is simplified the first piece all the way down. Now let's go back to 27. How will 27 break down? 9 and 3, good. 9 is 3 and 3. Okay, great. So there's already an 8 on the outside. Let me make this a little bit smaller. I should make that small too. Okay, there's already an 8 on the outside, so this is plus the 8. And now I have 3, 3, and 3 all underneath the radical. So I have 2 pairs of 3s, or I have 1 pair of 3, excuse me. So that 3 will come out, and I have a 3 that's still underneath. What is 8 times 3? 24, and then I have square root of 3. Do I have any like terms? Actually don't on this one. I simplified them completely. I was looking for them, whether or not they were like terms, but they aren't. So this is the simplest form that we can express it in, and we do have to work it down into that to know that I no longer can combine them for sure. Like I know for sure now. Okay, is that all right? All right, we have one more property. It's called the product rule for radicals. And I used this property before when I did it on the very front where I told you that the square root of 5 times the square root of 5 was 25, square root of 25. And it's true in general, as long as the indexes match. So like the nth square root of a, or the nth root, excuse me, of a and the nth root of b multiplied actually mean that I have the nth root of ab. This is very special for multiplication for products. Notice I didn't do anything like that on this last problem, right? I didn't say, hey, look, square root of 2, square root of 3, now it's square root of 5. I didn't do that. And in fact, it's not a true statement at all for addition. But it is a true statement for multiplication. It works for multiplication. So let's do some examples with that property for products. So on number 9, the thing that you have to look for, of course, is that the indexes match. On number 9, actually 9 through 13 that you see all on your paper, they do all match, right? Yeah, they do. So I can actually multiply what's underneath the radicals together. So I have square root of 3 and I have square root of 5. So what is this? Yeah, square root of 15. Right? Sure. Now number 10, I could do the same thing. I'm going to show you how to do this in 2 different ways. You can actually use the property of products, right? That product property right away if you wish. I can write down that this is the square root of 6 times 15, and I can actually multiply 6 and 15 together. So let's do that. What is 6 times 15? 90. Okay, but I do not get to leave the value as square root of 90 because it simplifies. So I need to divide it back out. And if you notice, that's going to be the same 6 and 15 that I just did. At least that's one way of doing it. So it kind of feels like that back over here before I multiplied it out to 90, maybe I just should have factored it from there instead of actually finding the 90. Are you with me? So there's nothing wrong with finding the 90. It's just that now I've got to go back down to breaking it apart. So if I break it apart, I've got 2 and 3, and the 15 is 3 and 5. So now I have the square root of 2 times 3 times 3 times 5, and I'm looking for matching pairs. What matches? The 3's. So it comes out. I have a 3 on the outside, and then I have 2 and 5 underneath, which makes it a 10. This is 3 square root of 10. So instead of multiplying it out to 90, what I could have done is simply broken it apart over here. Does that make sense? The multiplying to 90 was sort of an irrelevant factor. Now, if it had been a beautiful number that came out, like let's say we multiplied the numbers and it came out to square root of 100, that would have been great, because the square root of 100, I know that one, it's a perfect square. But they usually aren't perfect squares when we multiply them out. They could be, but they usually aren't. So let's try another one, number 11. So you'll notice on number 11, I have the same radical index, of course, right? They're both square roots. And they don't simplify in and of themselves. One of them is 5z, the other one's 2z. But I do have the ability to combine them underneath. 5 times, let me actually write this way, 5z and 2z. We'll just go like that for now. Okay, there's a 5, there's a z, there's a 2, there's a z. Do I have any matching pairs? I do. What do I have? The z's match. So I can pull a z out, but this time I can't pull any numbers out. I still have a 5 and a 2 underneath, which leaves me with a 10. Kind of like the 10 on the last problem, still being underneath there. And that's as far as we can go. Okay, you ready for 12? Okay, shifting gears a little bit. What do you notice on 12 that's different than any of the problems we've done so far? There's parentheses, and what else is there? Addition. I have parentheses and I have addition. Now, we did have a property of real numbers back, I think it was in section like 1.6 or something like that. And we said that when I have real numbers, I have this property called distribution. Do you remember that one? Okay. So that's actually what's happening here is I have distribution. So I can distribute this square root of 7 across the parentheses. So I'm going to actually write out what I get. Square root of 7, square root of 5, plus square root of 7, square root of 7. You don't necessarily have to write that step out if you can sort of see it without writing it. I'm okay with that. But if it helps you to see it, you can write it. So you see square root of 5 times square root of 7, and what is that? Yeah, square root of 35. And because 35 is 5 times 7, there's no matching pairs. But on this one, what's square root of 7 times square root of 7? Yeah, it's square root of 49, but what's the square root of 49? 7. So either you can write the square root of 49 and then simplify it to 7, or if you happen to recognize the fact that square root of 7 already has those matching pairs, you could simply pull the 7 out and write it as 7. This is what we would have as our final answer on that particular problem. Okay, 13, same idea in the fact that I've got the parentheses and the addition, so I've got the distributive property going on. The part that makes 13 different than 12 is that you'll notice that on the outside, I don't just have a square root of a number, I have 2 times the square root, right? So I have both a number on the outside of the radical and a number underneath the radical that I have to contend with. So I'm going to do the distribution property and write it out again. But again, you don't necessarily have to if it doesn't help you to see it. But I have here 2 square root 5 square root 15 plus 2 square root 5 times 3. Now, the numbers that are on the outside get multiplied. The numbers that are on the inside get multiplied. So on the first piece, there's only a 2 on the outside, so it's going to stay on the outside. But the pieces that are underneath the radical are going to be multiplied. Now again, it's really not super helpful usually to do the multiplication. It is 45. If you really want to multiply 5 times 15, you get 45. It's okay. But you're about to have to break it down anyway. So I don't know that that's super helpful. Is it? Did I do that right? No, that was 3 times 5. Or 3 times 15. What do I get? 75? Yeah, it's 75. Sorry about that. Yeah, so 75. Not real helpful to actually write it as 75. So I'm going to leave mine written as 5 and 15. The other piece, you'll notice that there's 2 pieces on the outside, the 2 and the 3. So I'm going to multiply those 2 together to give me 6, and there's only one number that remains still underneath the radical. Okay, 5 times 15, well, 5 is already prime. 15 I can break down into what? 5 and 3. So this is 2 square root of 5 times 3 plus 6 square root 5. Do you have a pair? We do. Those matching 5s get to come out with the 2. So now I have 2 times 5 on the outside. Again, you don't necessarily have to write it there. You could write that as 10 if you see it automatically. If you need it, write it. I end up with a 10 square root 3 plus 6 square root 5. Can I combine them? No, why not? Yep, the radicands, the number underneath the radicals, they're not the same. One's a 3 and one's a 5. So I have to stop at that point. Any questions on that one? Okay, so we had a product rule for radicals. We also have a quotient rule for radicals. The quotient rule for radicals says the following. If you have the nth root of A over the nth root of B, you could write them all underneath the nth root together, nth root of A over B. And sometimes it's easier to simplify them if you do that. All right, so the next couple of questions have to do with division with radicals involved. They're different than one another, but the first one looks directly like this particular property. It shows that I have a square root of 3 on top and a square root of 75 on bottom. Now, while square root of 75 does simplify, and we could simplify it out that direction, it's actually a little bit friendlier to simply write them underneath the radical together using that property. And the reason is because the 75 and the 3 both reduce by the same value. What can I divide them both by? 3. Okay, I mean, if it's anything, it's got to be 3 because that's the only thing that'll divide the top. So what is 3 divided by 3? 1. What's 75 divided by 3? 25. Okay, is everybody good so far? Wonderful. Now I'm going to use that same quotient property the other direction. I'm going to separate the radicals back out. You don't necessarily have to do that step, but I do think it's easier for us to see what happens if we have it written that way. What's the square root of 1? 1. And what's the square root of 25? 5. This is 1/5. Nothing underneath the radical was left actually in this one. So that was actually nice. Nicer than most of them have been on the ending. All right, 15 doesn't have a radical over a radical like 14 did. It doesn't look the same at all, actually. But what I want to show you is how you can, in fact, still reduce and simplify what's here. So do you notice how you have addition in the numerator? One of the properties of fractions that we discussed back in sections 3 and 4 is the ability to sort of get a common denominator and mush fractions together, right? Add or subtract them. We also have the same ability to take a common denominator fraction like this one and separate it back out. So if I were to do that, this would be negative 25 over 5 plus 15 square root 3 over 5. So I'm taking the fraction and I'm breaking it apart into two separate fractions. The reason that's friendly is because each of those has the ability to divide by 5. So what is negative 25 divided by 5? Yeah, negative 5. And then if you take a look at the 15 square root of 3 over 5, the 5 in the denominator only simplifies and only needs to simplify with the part that's on the outside for it to actually work. Kind of again like what we were dealing with scientific notation, right? We put the whole number parts together and we put the parts with the exponents together. Same thing here. So what is 15 divided by 5? 3. So it's 3 square roots of 3. Okay, so we are stopped at that point. We cannot combine the negative 5 and the 3 square roots of 3. They're not like terms. One of them has a radical, the other one doesn't. So at that point, we're stopped. Any questions on that? Okay, we're going to look a little bit more at radicals with the division in the last 4 problems. But the question here becomes quite, not quite different, but a little bit different of an argument. So we're going to talk about what's called rationalizing. If we had square root of 3 over square root of 7, we know that we can write that as the square root of 3 over 7. That's the quotient property we just looked at. But neither one of these is actually a simpler way to write this, because you can't simplify it any, right? They're both just ugly. Having a radical that remains in the denominator is often not desirable. So typically what you hear when you hear people talk about rationalizing is they want to rationalize the denominator. What rationalizing the denominator means is getting the denominator to have no radicals in it. So this phrase, rationalizing, means to eliminate radicals. And usually we do that with wanting them to eliminate them from the denominator. Okay? There are occasions in some of the higher level maths that I work with in calculus where we rationalize numerators, but that's definitely not the norm. It's almost always rationalizing denominators that we're trying to do. Okay? So our directions, in fact, say that on the next 2 problems. Rationalize the denominator and simplify. And we're going to take a look at that exact same question that we had above where we had the square root of 3 over the square root of 7. So when you have a denominator that is a radical, like this one, that doesn't simplify, right? Square root of 7 doesn't simplify. You multiply it by itself. Yes, good remembrance. So we're going to multiply it by square root of 7. And the reason we're going to do that is because that denominator, square root of 7 times square root of 7, will simply become square root of 49, which is 7. When we multiply a denominator, when we multiply a radical by itself, right, square root of 7 times square root of 7, square root of 3 times square root of 3, square root of 15 times square root of 15, it becomes the value that we're multiplying by, the 15, without the radical. Now the numerator doesn't become quite so friendly, right? Square root of 3 and square root of 7 don't have that same property. They don't match. So what is square root of 3 times square root of 7? It's the square root of 21. Now, I would be really hard-pressed to tell you that this is a nicer looking radical version than what we started with. I don't necessarily think that it is. But it does accomplish the directions, which were to get the denominator to have no radicals in it. Are you with me? Also notice, I can't sort of say, hey, look, there's a 21 and there's a 7. They both divide by 7, so let's just divide them both by 7. You can't do that because the 21 is underneath the radical and the 7's not, right? They're in different locations. So I can't simplify them the same way that I simplified, say, over here with the 5's, right? The 5's in this problem were both on the outside of the radical. I had the ability to divide each of the values on the outside of the radical by 5. I don't have that here. One of them's underneath, one of them's not. So this is the most basic form of this particular answer that we can come to. I can't make it any simpler. Okay? Now, on number 17, I could take the square root of 3 and the square root of 24, like separate them out. Like I could do that kind of like the first problem on number 14 or 16 was, right? I could do that. But it's actually a little bit easier if I try to reduce it first. So what do you notice that 3 and 24 can both be reduced by? 3. So the first thing I would suggest actually is to divide them each by what they can be simplified by. So this would actually end up being the square root of 1 over 8. Okay, everybody good so far? Okay, we're going to break it apart now then the way that we would have anticipated with the property of quotients. So I've got 1 over square root 8. Okay, everybody good so far? Okay. So I could do a couple of different things. If you want to multiply by square root of 8 on top and the bottom, we can do that. Do you want to do that? Sure, let's do it, because that's what it kind of looks like the last problem. I've got a radical in the denominator. Let's just multiply by it. Now, without a doubt, that will give me no radicals anymore in the denominator. It's just an 8. Are you with me? But I'm not actually done on this one. Why not? What's that? It's not because they're the same number. It's a good thought, but it wouldn't be the same. If I had them both be 5's, like let's say I'd gotten to this point and it looked like that, this would be done. But this one is still not done. All right, so the 8 itself, it isn't so much just that it's not a prime number, but it's the ability to be able to reduce. Right? I actually stopped right here and 21 wasn't prime, but I didn't have the ability to reduce the 21. I have the ability to reduce the square root of 8. So we're going to keep going from here. The number of 8 divides by what? 4 and 2. And 4 divides by what? 2 and 2. So, let me shift that up just a little bit further. What's that? Okay, so I didn't say we didn't reduce it because it was in the square root. What I was talking about on this one up here is the reason this didn't reduce is because the 21 is 7 times 3, but they don't match. But the next one that we're just doing right now will. So take a look on this one, how it looks a little bit different at the end. I have 2 times 2 times 2 here, and I have matching pairs that come out. 21 didn't have that going on for it. I just didn't have any matching pairs to come out. So on this one, the 2 will come out. There's still a 2 left underneath, and I have an 8. Yeah, but then this one's kind of like over here with my 5's at the end. I have a 2 on the outside and an 8 right here that both are even, so they can both divide by 2. So I'll end up with square root of 2 over 4. Okay, is that all right? A lot more reducing going on that one, just because 8 has the ability to break down and 21 didn't. Okay, there's one more difference that we haven't seen yet. Different feature. It involves the word or the idea of a conjugate.
Okay.
Yep. What's that? Told you this is a long lesson, right? Can't say I didn't warn you. Are you good? All right. Conjugate. All right. If we have the number a plus square root of b, then the conjugate is a minus square root of b, and vice versa. The reason conjugates are special is kind of like why square root of 7 times square root of 7 is special. When you multiply them, you eliminate radicals. They contain no radicals when you're done. Now let me actually just show you real quick why that happens. Sorry, I wrote that wrong. So if I were to multiply this out, an acronym you're probably familiar with is the acronym FOIL, first, outer, inner, last. If you're not, what this is it's binomial distribution. I'm just doing the distribution property. So I'm going to multiply a times a, that gives me a squared. I'm going to multiply a times the negative square root of b, which is negative a square root b. I'm going to use my inner terms. So I'm going to multiply the square root of b times a. That's positive a square root b. And I'm going to multiply the last terms together, which is negative square root of b times square root of b. What happens with the two that are in the middle? What's that? They do combine. What do they specifically combine to? Nope. Caleb, I think you're saying it. They have the same thing. This is negative a square root b and positive a square root b. They cancel out. They're exactly the same thing. One's positive, one's negative. They add to 0, or they combine to 0. So the part in the middle is a big whopping nothing. Now the a squared stays here at the beginning. That piece stays the same. Notice what happens at the end. What's square root of b times square root of b? That is just b, right? Just like a moment ago, square root of 7 times square root of 7 is 7. And so what I want you to notice is there are no radicals left when I do this. And that always happens with conjugates. The inner term and the outer term that were multiplied, they add to 0. The first term gets squared, the last term gets squared. So let's take a look at how we can use that to rationalize denominators. Directions are the same as before. Our goal is to not have radicals in the denominator. The problem is that these denominators have addition or subtraction in them instead of just being a single radical. So what I need to do is I need to multiply them by the conjugate. So the conjugate to 5 plus square root of 3 is 5 minus square root of 3. In the numerator, I'll distribute, and I will get 5 times 2 is 10. And then 2 times square root of 3 is 2 square root of 3, and it's subtraction. So I definitely still have radicals in the numerator left, typically speaking. But in the denominator, the first terms, 5 times 5, 25. But then when I do the inner terms and the outer terms, they match, but with opposite signs. One is positive 5 square root of 3. The other is negative 5 square root of 3. So they add to 0. My last terms, I have positive and negative. That makes a negative. And then the square root of 3 times the square root of 3 is 3. The pieces in the numerator, the terms in the numerator are not like terms, so I cannot combine them. But in the denominator, I have 25 minus 3, which is 22. Yes. And there's one piece that I can finish up dividing here. These three numbers are all divisible by 2, so I can divide them all by 2. So I have 5 minus, you can put a 1 here if you want, or you can leave it off, square root of 3 over 11. Okay, I know we're like pushing the limits here. Let me finish the last one for you really quick, and then you go back and watch it in more detail later if you need to think through it again. We're still doing the same thing, multiply by the conjugate, 3 square root of 2 plus square root of 5 on top and bottom. We'll distribute out the numerator. That gives me 18 square root of 2 and 6 square root of 5. The denominator, the first becomes 3 times 3, which is 9, square root of 2 times square root of 2, which is 2. The inner and the outer cancel, right? So this piece and this piece are exactly the same, but opposite signs, they always will add to 0. So the other piece is the last two pieces multiplied, which should be a positive and negative, so negative. Square root of 5 times square root of 5 is 5. So I have 18 square root of 2 plus 6 square root of 5 over 9 times 2 is 18. 18 minus 5 is 13. Did I get that right? Yep. And 13 does not divide with the 18 or the 6, so I can't actually divide anything out of those pieces, and I'm done. All right, this lesson's going to take you a bit. All right, homework, probably an hour or two. I'm just warning you right now. So make sure you don't try to do this right before you come to class on Tuesday morning. You won't get finished. All right? Have a great weekend, guys.